Hello world, and welcome to another episode of We love to talk about exciting subjects in science, medicine, robotics, astronomy, futuristic ideas, music, or anything interesting in the news. So let's get into it. Did you know in the news? MIT researchers have developed a camera-based touch sensor called Gel Sight SLEF. If I said that incorrectly, please forgive me. Which is a long, curved, and shaped like a human finger. Now, this finger-shaped sensor provides high-resolution tactile sensing over a large area, enabling the robot hand to perform a variety of grasps, including pinching grasps and power grasps. The sensor design uses two mirrors to reflect and refract light towards a single camera located at the base of the finger, allowing it to see along the entire length of the sensor. Now, the researchers have also used machine learning to estimate the force applied to the sensor base on the sensor's bending. Now, this technology opens up new possibilities for robots to perform different manipulation tasks and enhances their dexterity. In the future, the researchers plan to make more sensor articulated and capable of bending at the joints to mimic human fingers more closely. So what do you think about this? I guess this is pretty cool. I see everything coming together with all these videos I'm making. They're practically building a humanoid. Now, for all those techies that want to know a little more, I'm going to leave a video here that goes a little more deeper for those that are very techy. Now, I'll talk to you soon, but until then, stay safe.
Hi, my name is Alan Zhao. I'm a PhD candidate from MIT. In this paper, we introduce Dexterous. It is a tactile robot finger that is curved, compact, shaped like a human finger with both proprioceptive and tactile sensing capabilities. A lot of camera-based tactile sensors have been introduced in recent years. Compared to resistance, capacitance, magnetic, or other kinds of pressure sensors, camera-based tactile sensing has the advantage of being able to produce high-resolution geometries of the contact with a very low cost. However, the imaging and illumination system, as well as the supporting mechanism, all take space. For this reason, it is usually easier to make camera-based tactile sensors as fingertip sensors, and it's generally much harder to apply camera-based tactile sensing technology to a large sensing area. One common way to achieve a large sensing area is to put multiple cameras at different sections of a finger to cover the inside of a long finger. Another way, as the OmniTouch sensor did, is to put 5 small cameras inside a dome-shaped shell to cover many directions. It is also possible to only use one camera inside a cone-shaped finger, as the inside finger did. But this way, the camera looks at the contact surface at a pretty sharp angle, and the fingertip appears very small in the camera's field of view. So we want to ask the question, is it possible to design a human finger-shaped, large, and curved camera-based tactile sensor without sacrificing compactness and resolution? Our answer is Dexterous, a single-camera human finger-shaped tactile sensor. It has only 5 main components: a 120-degree field of view wide-angle camera, a 3D printed plastic backbone, 2 pieces of mirrors, 2 LED strips, and a cast silicon gel. The unique human finger shape of Dexterous is made possible by controlling the curvature and placement of the 2 pieces of mirrors. Mirror 1 is a curved piece of mirror that is parameterized as a B-spline, while mirror 2 is flat. By shooting a beam of light from where the camera sits, the light could reach all the way to the tip of the finger after 2 reflections. In fact, through refraction and reflection simulation, we made sure that the entire sensing surface of the finger, which is the surface facing inside, is all covered by the single camera's field of view. We also made sure that the density of the reflected light beams is relatively uniform, which means we still maintain high resolution even at the tip of the finger. The resolution is around 30 pixels per millimeter at the bottom of the finger and 20 pixels per millimeter at the tip of the finger. Here is a real sequence of tactile images that the sensor is able to capture. Here we press a M8 screw onto the finger. The screw measures 8 mm in diameter, and the pitch, which is the distance between two adjacent threads, is 1.25 mm, which can give an idea of the resolution of the finger. Besides tactile feedbacks, Jalset Svelte can also accurately estimate the net external torque applied on the finger, or the proprioceptive information. Because Jalset Svelte is long and thin, when external torques are applied on the finger bends in both the vertical direction and the horizontal direction. The idea is that we could track the deformation of the plastic backbone directly to estimate the load, which is far more accurate than doing integration on the tactile images, which is affected a lot by the viscoelasticity of the silicon gel. Because the two LED strips are rigidly attached to the plastic backbone, the movement of the LEDs is equivalent to the deformation of the backbone. We can easily track the LED movements from the tactile images. Then we train a convolutional neural network to estimate the net bending torque and the net twisting torque that are applied on the finger. Jalset Svelte is a long, curved, human finger-shaped tactile robotic finger. The unique shape and the sensing capability over a large area makes it now possible to design robot bending factors that are dexterous, compact, and cost-effective. For more details on the finger or our implementation of a robot hand with Jalset Svelte, please check out our paper or our project website. Thank you.